Why, hello, class. Welcome to EB 510. Glad you're all in attendance. Okay, welcome back. I know that might have been a bit rough last time, but I hope you slightly appreciate more those governing equations we have to speak of throughout the whole class now. So I like that as the stage is set. I went overtime last time, so I did not actually get to talk about this extra credit type of thing, so I'll talk about that right now real quick. So you might have noticed that I sometimes blurt out some extra credit questions here and there if I'm on a kick on a lecture, and I'll mention like just work those math details out or something like that, right? So you might hear this phrase heard, or sometimes you might see it on notes. So you might hear it or you might read it in notes. So I give kind of extra credit two ways. So I'll either say it in lecture just randomly, or I'll put it in the notes and then I'll just remind myself. Okay, so the rules of the game for extra credit are this. It's a first come, first serve basis for the extra credit. Because I don't want everyone to attempt the extra credit. I give a lot of it throughout the term. So I don't want to be stuck grading like 3 times as much homework for every student because it's just me doing the class right now. Okay? So it's a first come, first serve. Okay? So that means, really what this means is the first student to post the solution just on the Slack channel will get those extra points. And then once that's done, it's off the table. So it's sort of a motivation of, if you watch these lectures, you hear extra credit, just work it out right then and there, and then post it, and you'll get the extra credit. But once it's on there, I kind of remove it. So right on that channel I track, I see someone put an extra credit there, and I have a little sheet, and I put your name to that sheet. Anyone else tries to answer that same problem, it's too late. You were too late on it. So it's kind of a speed thing on this extra credit stuff. And that kind of, I'm doing that to kind of train you to, so the point of the extra credit really is fast reasoning is the idea on that. It's very important to be able to quickly work out the details, because the details are really how you show the rigorous things, let's say in the math of calculations of why it is true, but the reasoning doesn't depend on the details. If you say the details are right, then you just go along with it and don't have to bore people with them, kind of like how I do these lectures, honestly, because there's so many tools out there these days like Mathematica and symbolic language. I don't really see a point to do those things for you. Really, you should all be instructed to figure out those tools and just speed up human reasoning. Okay, so I do that for training you to just quickly kind of find a reasoning's true or not, and just these details. You can do it any way you want, really, too. Actually, you can do it in Mathematica. So those are just the rules on this extra credit stuff that you might see me be describing right now. Another thing brought up on the Slack channel is this homework. So for that homework 0, which is the plan, there's no extra credit for submitting that homework in LaTeX because I want it submitted in a spreadsheet. My folder won't allow you to submit a plan that's not in a spreadsheet form. And the reason I did it that way is because I can just link this up with my grading sheet easier. So if you made a PDF, something like that, I would have to translate your plan calendar with mine. So speed up everything. For this homework 0, it has to be in a spreadsheet form. I think a Google Sheet form will work well, but you also have an Excel sheet. Yes. So then past 0, any homework submitted in a TeX file correctly submitted in a TeX file, you'll get those extra points on that homework. Okay, so that's sort of two things I want to bring up, especially on this extra credit thing. So sort of once these lectures are published, which I try to get them up by Sunday night. If there's a bad week, let's say, maybe it'll be Monday or something like that, but kind of bear with me on that. That I'm trying to get them up by Sunday midnight or by Monday. So once they're up, those extra credits are set off into the sea of student, and whoever gets it first will get those extra credit points. And then once somebody has the correct answer, then it's off the table. But there's a lot of it throughout the whole term, so I wouldn't stress too much of like, I need more opportunities for extra credit. You might know, I mean, the more lecture notes you see in many of these lectures you'll see, I will say that stuff a lot. Okay. Okay, so those are some minor details. But now let's get into kind of we're now in more fun part of fluids, or just any physical science, I want to say. This stuff is just magic, I think. Right? So a big topic, right, is just dimensional analysis. It seems so basic, right? But I really think, I mean, maybe hopefully I can share some examples with you on how this stuff, right, is just really, right? This stuff is just magical, I think. It helps you correct a grad student or a piece of homework because you'll know that a formula they have is wrong. It lets you, I should just write out some benefits of dimensional analysis, right? I mean, it makes, right? It makes equations right? You can rationalize the equation better if you see it in non-dimension because you've put all the dimensions in terms of parameters. And it helps with scaling your equations. If you just think about the dimensions occurring in your problem, I mean, this whole idea of scaling. I mean, scaling and dimensional analysis, I think, are tightly interwoven together, and we'll see that. But still, it helps reason this stuff as well, right? I mean, it helps you skip. This is the magical part about it, I think, is it's amazing to me how if you just pose the correct dimensional question, right, you can skip the actual solution step. So almost maybe if you understood 1 and 2 really well, and you can write out those system of equations, those Navier-Stokes equations, every single time for your problem, and then you can hit it with non-dimensionalization and the scales involved in your coordinates and even a time, you almost could solve any problem that way approximately. So, right, this is for approximate. Other things, I mean, sort of, you know, this is approximations, but also one other big thing, and I'll put this in red because maybe you guys are sick of me talking about the pure math of some of this stuff, of how, you know, the reasoning of it all coming down to, like, let's say some assumptions on. Wait 1 sec. Okay, I'm recording. I'm always afraid I'm not recording the mic, and never mind. You know, maybe you're sick of this math reasoning, and it's like, I don't care if it's linear, I don't care if it's symmetric, I don't care about you or your lectures. But what you would want is this one lecture, because dimensional analysis, even, right, I mean, this is just the basis, right, of all experimentation. Okay, so if you don't care about any of the fundamental math or the theoretical ways to get a solution to the problem, right? If you don't want, right, maybe in lecture 1, remember I had that curve of like there's data, there's numerical things, and then there's the actual theory, right? If you say, you know, to heck with the numerical scheme, to heck with the theoretical prediction, I just want to get some data points and see what's going on with that function. Well, this is just such a key thing to do first, right? And I think it's more intuitive, it's more physical. I mean, it even lumps, I mean, I think this stuff, right, it's like basically almost as good as machine learning. think it's really just almost as good as this design of experimentation you maybe took, which is a statistical thing of how do I have to compare so many different variables. All of this theory that we go over with maybe these examples, I think overcomes this. Even this topic, I think, is a really interesting concept, right? Where I have made machine learning algorithms, neural networks, to try to really do the same ideas of these Weber numbers, and they don't do it that way, right? So that's something I will talk about with this blood spatter one and other experiments that involve, like, well, combine it down to a function of Reynolds or Weber, and then I can see the dependence that way, right? This won't do that for you. This is a different way to describe the function based on data. And then, in fact, with this machine learning, if you did have to do it with your fluids experiment, right, you wouldn't even know what dependent variable you'd want to measure. Right? So machine learning comes after acquiring data. So I still think it's fundamental to do this whole dimensional analysis and this scaling and thinking about primary dimensions, right? Even if you want to do everything in machine learning in Python, which you can totally do, right? But the idea is prior to that, you still need to go through here. And it really is magical. Okay? How is it magical? Well, this is one of my favorite ones. And I have to liken this to I mean, originally it came from, I think it's a Taylor, G.I. Taylor came up with the example, but two of these come from someone named Michael Brenner, who is a Harvard professor, I think, of applied math, but he's hilarious. And I think I saw these randomly in one lecture, and I've never forgotten them in 3 years. Okay, it just seems crazy to me. So imagine you have, let's say you're a spy. Let's say you're a spy during World War II, and you have great reconnaissance and data, and you have a bunch of pictures with timestamps of the atomic bomb. And you just got tons of these. Okay? I draw a lot of pictures in this one, so I will take my notes. Okay? So you have a bunch of pictures, which are data, right? And you have a little timestamp. Let's say this one's 15 milliseconds. This one was 127 milliseconds. This one I have is 900 milliseconds. So you have a picture, and you have a timestamp on each picture, and you have an atomic bomb explosion. Okay, and it just seems to be like a little bit bigger here. Okay, and then each of these, right, I mean, you know that this picture has other data associated to it because you also have a length scale in every, right, you have, each picture was taken such that you have some sort of length scale in the image, right? So whoever was in your airplane, whoever was doing spy reconnaissance on the bomb, right, they did this well enough that they had a very good timer and they had a good reference point. Maybe there was a little ruler at some reference points of the pictures. I mean, I do that in my drop. I mean, I do that too, where if you take a picture, it's always good to put a ruler so you can create this reference length. It's a meter, not milliseconds. Meter. And this is your blast, right? And then also because from this, right, you can actually you can figure out, right, you could take a little ruler on your picture and just look at this radius, right, the radius of the blast. And you could even say, well, it's not really spherical, but you could just take like a diameter of the blast, the largest dimension, what's happening in the explosion, and just say like the radius is equal to, right, half of the diameter. You're okay to do that, however you want to do it. I mean, in reality, you could just say, here's my reference length scale. You measure something here and just measure the largest distance. I don't really care. Okay? And then the question that's given to you is how powerful is this bomb? Because they've been very secretive about the right? How powerful is that bomb? You know it's big, but can you tell me how much energy was in that bomb? And that's even another thing that maybe I didn't go over, right? It's the idea that, okay, as my spy, I'm supposed to tell you how powerful that bomb is. Well, power, I could measure power in terms of energy, right? So I just have a bunch of pictures, right? right? I mean, I just have a bunch of pictures, right? You could even make these points in data, but you could even just take one, actually, if you just thought about like the dimensions of this problem, right? So you have the idea that, what could you think? You could go, well, you know, for a closed system, that the energy must remain constant. I can neither create nor destroy energy. So, you know, you could go there, where however much energy I had at one point should be, like, I don't want to, right, the energy from here, right, if it started at some block of solid explosive, thinking about my closed system, I have to conserve that. So that means if this is equals 0, this isn't even necessary. I just think about this idea that E naught. So if it's just a solid explosive right there, then it blows up. You know, there's some associated internal or some energy density in this bomb. And you know that would be conserved throughout this whole time process. So I mean that's okay. I mean even this would get you off the bat, because if you know, wait a minute, so dE dt must be 0. So that means I'm looking for some function, right? Differential equations are ways to describe functions. So how powerful is the bomb? Well, I'm trying to posit then stuff I know. I mean, this physical law tells you that there's a function that exists where if I take the time derivative of the energy and I think of it as a closed system, it's equal to 0. So that means, well, this defines a function. So that means I'm looking for the function. So I want energy as a function of stuff that I know. Right? Time ticks along. So then what do you know? So this stuff I know. I mean, this is, what do you know? You have a bunch of pictures laid out for you. And they have some things involved in them, right? So I know the radius at a time. I know the time. I know the radius. And what else would I know? Well, there's something, right? I mean, it's like, well, there's other, right, the other thing about this stuff is you would have to then go, I also know that this is happening in air. So I know that there's a blast and it's occurring in air. And there are properties of air that I could look up. Okay? This is a step I think is non-intuitive, so I've pointed out. I've pointed out that you don't get this naturally. The idea that, well, I clearly see r in front of my face, and I clearly see time in front of my face. But you would need to posit that I also should consider the density of the air. How would you posit that? Well, you'd have to be a magical genius, but right, it's not that hard. If you imagine explosions, you might see an explosion underwater, and you might see an explosion in air. And clearly their blast radiuses are different. You ever seen a firecracker or a torpedo go off? It kind of boom, and then like it doesn't grow it's that quickly, right? There's just there's clearly a difference between the explosions in water and explosions in air. So that's a parameter that probably would show up in this energy function that I don't know what it is. Okay? So then you add your sort of density of air. So then we're starting off with this simple example where I just do crazy magical things because I'm at a loss and I'm just trying to make I'm just trying to make some prediction just based on data that I have. Well then, this is a function, so maybe you just go like, okay, so energy must be proportional to these inputs some way. Right? It's proportional to some combination of these variables. And one thing, if you just look at then the dimensions of this, right? If you just look at the dimensions of energy, right? What do you have? We have its dimensions of mass. Let me just get my notes, right? So if you just look at the dimensions of what energy is, right? It's going to be the dimensions of mass, a length squared, and then a time squared. Okay? And now, given everything you have on the input, you can just play around and go, well, I at least could match the dimensions of this function. So given things that I do understand and know, the rho, the rate, the time, I can go, well, I can combine these, right, to get the same units, right? I could take time, right? 1 over time squared gets me here. And what about here, right? and you have this situation right here. So then combining this and this, I'm going to have to get just an L squared. All right? And that is this rho. See if that works, right? Rho is what? It's a mass divided by a volume. That'd be my rho. To the fifth power, I need to get these lengths up on top. So then, right, that would be 5 of the radii. So I'd get rid of that power. I'd be left with L squared up there. And my dimensions match, just by a combination of the variables I have. So you at least posit that, right? And then you have to put, and then you put this little symbol there right now, because you've made an assumption on how this function is going to look. You did some wiggly diggly stuff, but you've at least then combined these arguments to match the dimension of what you posited, right? So what did we say? So with this, you go, well, it's proportional then to a rho to the fifth over t squared, because you were asked that question of what's the energy. Well, that's fine, but it's not. This is the idea where the experimentation comes in, because well, that's fine if you would do that, but is it true? Well, you have a way to maybe test this now, actually, right? You could then blow up something that you do know about and take the same pictures. You could then compare them and see that. But this makes a prediction right at the same time. You could track then the radius function. This is clearly moving with time, this r of t. It's an r of t. So you almost have a, right, this makes a prediction on that the radius of the blast, okay, you have 1/5 power on the radius, right? So this is actually a way you could, right? Now you could figure out what this, right? Now you actually could figure out maybe what this is by fitting it to your data. Because you have a bunch of pictures, right? And you do know what the radius is. You could maybe match it then to see what this number is. Again, you know what the radius of air is. You can look it up. And then each of these timestamps is actually still measured, right? I have the timestamp here. So this proportionality means, right, proportionality, sometimes you can think of it as an equality by a constant that I don't know about. Okay? Now that's weird, I think, especially for the fact that this is right. You can solve this explosive problem in spherical coordinates, right? And with the correct assumptions, you would calculate what the radius is, and you get this relationship. The only difference is analytically what happens is you can actually determine what that constant is. And I think it's like ends up being 1.1 or 1.2. But you know how hard it is to solve this thing in spherical coordinates analytically, especially back then when Taylor did it. It's incredibly difficult. But all I did is I just said, I want some energy and I'm positing a function that gives me the energy. And what's the stuff I know? Intuitively, I clearly saw time on the picture, and I clearly see the radius of the blast on my pictures. I then maybe just had to say, well, what's the density of air? That will also depend. And then I just matched units. I said, well, the only way I'm going to get units energy here with a combination of them here is by doing this. And I think the process of just trying to match them with algebra and just doing it by hand is important, right? Because you can just play around and make it work, and you'll get this. You can go ahead and try other ones, right? But this does get to this idea, maybe later, with this Buckingham pi theorem stuff, which is maybe important for if you're just tired of doing it, okay? So again, right, the idea is this is basically true. It ends up being true in the solution to the expanding radius of this blast, which is modeled by the continuum equations that we have, if you did that work. But just for my dimensional analysis, and then I can tell you the bomb is this powerful, just on this and just on the data that you gave me. weird, magical. But now, how about another one? So here is another example of blood spatter. So you're on a crime scene, right? And there's a bunch of blood spatter everywhere. There's no body, you just have a bunch of blood drops everywhere. You're trying to see, was there a gun, right? Were these blood spatters caused by just blood falling off the victim? Or was it clearly done by a whipping weapon approach? Was there a gunshot that made these blood spatters hit the wall with a lot of velocity, right? Now you have a bunch of pictures. Again, you just have some data. Okay? For the most part, you have a bunch of blood splatters. Maybe that look like they're sort of just spherical. Can you see? So you have sort of group, sort of most of them. Let's say group 1. Right? And these are photos. Again, in your photo, you have a length scale as well. Pretty small, let's say. So that's 1 centimeter I think I've drawn there. And that would just be in your photo an average diameter of the blood drop that you've seen on the crime scene. And you're trying to say, was there a gun present? Was there a weapon present just based on the blood spatter, or was there not? Okay? And then there's one that kind of stands out of these blood spatters that you take a bunch of pictures of, right? And there's these ones that have like a lot of splines, they're called, or fingerlings coming out of them. Okay? And what you do here is you would just count the number. You would just count the number of fingers in your image of these blood spatters, right? So let's say here, maybe you saw one every once in a while. In group 1, there was mostly, you had an average of like 1 to 0 number of blood splines. The splines being the little fingers. And then in this case, for group number 2, you would say, well, I had an average of 16. 16 splines seem to be in this very large, very fingerling blood splatter, right? Fingerling blood splatter analysis. And you have no theory about anything right now. This is a solved problem. You can look up the equation that tells you like how fast the blood was dropping, but let's get there. Let's get there. Let's imagine you have all the money in the world and you're in your investigative mode and they say, you can run any experiment. You just got to tell me what happened that day. And this picture has its own diameter. Well, so this also has a length scale. Let's say it's like 2 centimeters. It might be slightly different. All right. So you have some properties. You know that in group 1, I sort of have a small, right? It's small diameters. They have low number of fingerling. A larger diameter or average diameter based on the group 2, which clearly are like the largest. So there's some separation occurring right there. And then in this case, right, you have a large number of the splines in there. Okay. So with these images, now again, we're trying to make some predictions based on the variables that we know to be true in this crime scene that we have. All right. So what's the easiest variable in these images I have that's observable? Right? Is D pretty easy to observe? Some could say that, yeah. I mean, you could have a software that would just look at your image and see, and it'd be an edge detection, let's say, and just spit out a random, right, some arbitrary D. But I think there's the most observable part of these pictures is the number of fingerlings. It's just 100%, just non-arbitrary. It's a picture in front of you, and you just count them up. You just count up the number of fingerlings. Anyone can do that, or blood splines. You could have your grad student do it. You could have the low-level intern do that. It's very, very dummy-proof. It's just the number of fingerlings. So I would say for any sort of experiment I would run that would try to see how velocity of blood depended on how this looks in the end, I would pick N. Because N is very easy to observe, which gets into maybe like a a recommendation for this unit analysis stuff of when you're trying to posit an experiment is the output of your function should usually be very, very easy to observe, right? It makes your life easier. So just as we did here, this output was motivated by a question of how powerful is the bomb. Okay, I want a function that maps things I know to the answer I'm trying to get at. This example, we didn't really have that yet. We just had photos of blood spatter, and we were wondering, can I tie in velocity of blood drops to this somehow? Okay, but we didn't know what the output was. And I'm saying there's just a natural choice, I would think, where it could be d, it could be n. It wouldn't matter. But that we're then in the hunt for this function, a function that spits out the number of blood spatters. Okay, so again, stuff I know. This is kind of different though, because now there's a bunch of other parameters in the situation that are non-intuitive. Okay, so what do you know? What do you know about these images? Well, directly on the photo, this is mapped. I have at least the diameter of the image as well. Then other physical intuitions you have is then there's all these other properties of fluids that we're talking about that probably govern whatever happened. I mean, think about what happened right before this blood hit the surface. Okay, you had some you had some blot impacting the surface, and then eventually, it hits this look right here, and then it settles down. Right? So you had velocity, so you had some velocity involved in there, and that's what we're also looking at. So let's say there's some scale v, some v naught velocity, some characteristic velocity of how fast this has hit this plane right there. And then you also would need just the properties of the fluids themselves, right? So blood has fluid properties, and those should maybe always go into your function that you're looking at, right? Blood has a viscosity, it has a density, and then it has something that maybe you've never heard of before, but is still an inherent property of the liquid I'm talking about, and that would be something called surface tension. So now I have more parameters, right? So why would you, picking surface tension, why would you include that in the function? Should it depend? Well, at least in this image, you see that it involves the stretching of a fluid surface. It's a little drop of fluid, so then when it hits here, it's clearly going to involve and stretch out this fluid surface against the platform. And that's exactly what this measures, right? A surface tension is the force involved with how much this drop of liquid wanted to stay together, where this splining clearly involves, I think, some level of the surface tension. Now, does the density matter? Does viscosity matter? Well, we may not know, actually. So go ahead and keep them in there. So then we have another situation right here where now I have my output, which is the number of splines, as a function of all these dimensional variables. Okay. So if I want to do the same thing here, ideally, maybe you're getting to a point when you just want to say it's equal to something, maybe the addition or subtraction. You would need you would need the units to cancel out, where this has a unit. So you need to combine these units to actually make a no units on this side. It's still kind of shaky, but we're just experimentation people. We're just looking at how units work around and how we can figure out this case. At this point here, you actually could stop, and you could just use the Buckingham Pi theorem, right? You can write a program that does it for you even, where you just posit a bunch of stuff in a function, right? It takes work to say, I want my function to spit out the number of spines, and then you have this list of variables, all with dimension. And then the Buckingham Pi theorem or technique is just a way to lump them all together. And it does it for you automatically. But you don't get much sense of how to scale it yourself. Okay. So how are we going to do it? Well, we could look, right, we can look directly at these dimensions, right? So first you could start with, I have rho, so I have a unit of mass, right? Primary dimensions. There's the idea that there's a primary dimension. I just have mass, I just have length, and I just have time. Okay, not derived. So then what is sigma? Maybe you don't know what sigma is, right? But it's a force divided by a length, right? It's a Newton per meter, right? It's a Newton per meter. You give me a dimension of stretch, and I'll tell you the force that occurred there. Okay, then you go, what's the force? Then you have this, a force is ma. So think of ma as being a unit of mass, and then a being a unit of what? Length divided by time squared. So this has units of length right? Or this is the force part, m times a. Acceleration is L divided by t squared. So then, right, that cancels out. So now you have, right, these primary units of sigma. And you have these units. What's viscosity? How would you get the units of viscosity? Anybody remember? There's no class here, actually. I don't know why I'm doing that. If you ever forget the units of viscosity, right, you can always go to that definition, right? We said for our Newtonian fluid, right, that the shear right, in general, we are making this assumption that it looks like this. Well, then you just do the unit analysis on that, right? And then you can see that this has units of mass. We have mass times length. And then what's right? The unit of velocity is going to be a meter over meter. Right, velocity is length over time, and this is just length. So what are good scales for the primary dimensions? That could help, right? So these are just all the components I have. Again, so you have this is a unit of length, and then the velocity is another unit of length, and then of time. So now there's a bunch of techniques for doing something like this. There's also just ways to combine these things, but you could also just get around by eliminating each of the primary dimensions by dividing them by a scale dimension. So what's a great, what do we have as a good, so for instance, if I want to, what is the length scale like? Right? I think that's a good, right? You could have a choice of just the diameter, right, of the droplet. There are other ones you could do too, right? So this is just a choice I've done saying, well, the primary dimension of length should scale like this diameter of the droplet I have on there. But there are other ones too. You can just look at this and see, well, what do I have? Whoa, ooh, I can get one here, right? Yeah, so you can combine these to actually make a length as well. The velocity too. There's a bunch. And I think you can play around with them. I besides doing a bunch of attempts on this board, I think at this point it's kind of fun to just play around with these dimensions and try to get a reasonable thing. Certainly, you could just start with this. I'm going to scale my length dimension by d. So that means this would be divide everything out by a d. So right here, you'd have 1 because I have d divided by d, and then right, so now this is of units 1. So now this has no units. This is 1 over time. Then what was the viscosity? This would have to multiply by this by the idea is eliminating each of the eliminate each of the primary dimensions in this formula by what you've chosen. So this was a dimension of length. I've divided by d to make it 1. Here, right, I've scaled this length by d, so now I have the unit of 1 over time. For viscosity, if I want to get rid of that, right, I would multiply by a dimension of d. Okay. Then you have what's a rho, right? So then you have rho, which is numeral t. Yeah, what am I doing? So then here times d, and then you have rho. Boom. And then what was sigma? Sigma has the units of the length. It seems like clunky, and it is. And sigma doesn't have length in there, actually. So I guess you could leave it alone. Right? Now this has just a unit of mass in it. And this has mass. Okay, and now these are the primary dimensions. Notice I've eliminated this primary dimension of length in all of these arguments. So I'm sure you can see now. Well, now search for what's the scale of the primary dimension of mass, and then what would be the scale of the primary dimension of time. And they're just choices that you have to make at this point. And this is what's hard about, I think, this, is we don't have a governing equation to scale like we did with the oscillating U-tube, right? We don't have something informing us. We're just going off primary dimensions and going off the cusp on it. So it's hard. It's clunky, right? But you can just keep at it and keep at it, right? So for instance, on this one, how would we eliminate the time? Right? How could we eliminate the time on this? Right, I have to multiply by a unit of time. So what's a good time scale? What's a good time scale, right? Those seem familiar to you? But I think I'm just gonna jump to the idea on this, that you have rho. You end up getting these groups in there, which are a rho. And these are non-dimensional, right? And these come from choosing scales for your primary dimensions of mass and your primary dimension of time without any equation to go off of. I'm probably doing you a disservice by doing this. Okay. Because there's two different ways to do this. You could have had this one or this one arise, and everything else would be non-dimensional. But that didn't go as well as I wanted it to. I'm not redoing this one, though. I'm tired. So you have then just this statement here, that the non-dimensional number of splines is equal to these two parameters that you can find, which are non-dimensional in the arguments. Okay? Without any explanation of forces at all. Maybe you got this with Buckingham pi, where you reduced it down to just 2 inputs as opposed to 5. I mean, we went from 5 inputs down to 2. Okay? And that will always be the case because, like, Buckingham pi theorem basically says you have 1, 2, 3, 4, 5, right, 5 inputs, but each of those inputs dimensionally, right, has to be comprised of a mass, a length, and a time unit. So 5 minus 3 is 2. Think of it that way. Buckingham pi says if you have 5-dimensional arguments, if you want to take away all the dimensions and have only unique dimensionless groups, it would be 5 minus 3. So I have 2. So these have names, though, is what's important. And one thing about this is it could have gone either way. I mean, you could be flipping it above, right? This is 1 over a Reynolds number, right? But we just kind of write that as a function. So that means you've posited that the number of splines is a function of maybe a Reynolds number and something called a Weber number. This is associated as a Weber number, right? And it's a Weber number because it's a measure of kinetic energy of inertia over the kinetic energy or the surface energy. Surface energy being, right, surface tension can be thought of as a surface energy as well. In fact, even the same number, right? So that's what this Weber number represents. You all know the Reynolds number is a ratio of inertial forces to viscous forces. So the number of splines is some function that's dependent on, well, is it a very inertial process or is it a very viscous process? Does blood look like honey or does blood look like oil or something like that? And then there's this new one you find called the Weber number, which is a measure of something probably that should be more intuitive, right? More intuitive, that this Weber number is a ratio of kinetic energy to surface energy. But you don't really have much else to do right now, so now you run experiments. You've been given infinite money, or at least better money, and what you've done already is you've saved money by not having to vary 5 things. You now only have to vary 2 things. And in fact, you may not even have to vary this one if you just calculated the Reynolds number of what you think it's going to be. I mean, this number is not going to matter much because, right, blood isn't the most viscous fluid at all. But you could just you could just make the experiment and populate a graph now, right? Or here'd be my Reynolds axis, here's my Weber axis, and now I'm just counting. It's a fairly easy experiment, I would say. You take a sheet of paper and you just drop, right? You take a sheet of paper, you take a little slice image of the droplet right before it hits the surface, so you have some camera that's just looking right where you drop the surface, and you just measure all these properties, right? And it could be different liquids, it could be different quantities of whatever you want it, and all you're doing is you're counting splines of the spatter. You could keep it all as blood if you wanted to as well. And then really what you would find, right, you would actually end up kind of seeing that this makes some sort of surface, right, where this is sort of constant. Right? It kind of ends up looking like a surface like this. At least interpolating all your data points, you would see some match of a surface that looks like this. So imagine this is sort of like a curving up surface. But importantly, you see that there's not much dependence on the Reynolds number if you took the data. You could make the same argument if you were going like, I don't think it depends on this. But if you made the graph, what really you'd be seeing as, right, partial n over partial Reynolds is essentially 0. Variations in Reynolds seem to not make that much of an effect for n. Why does that matter? Well, it matters because then you can throw this argument out based on your experimentation, based on this idea that the surface, the partial with respect to that argument, 0, is basically flat. These are just flat lines moving up along. And that just gives you now a much, much better graph to put in your report, right? Now the graph that you have to give is really just this, right? It's just a function of Weber numbers. Okay, so here's n. And then you would just see what the function looks like. It ends up being a function of Weber to the 1/2 power. So it looks like this, and it ends up being a 1/2 there. So let's say this axis then, I call it the square root of a value. That's just to make this like a, it's just to make it look like a line. right? So this Weber, go this way, Weber to the 1/2, right, it's right there. So now I have square root okay, so this to the square root is actually this value right here. So you could actually think about this as this axis is just going to be a line with here's velocity, and then the slope would be that for a given fluid. But that's your experiment, and that's what's great, right? Whether it's Weber or not, I'd like to just think of it as a Weber number, the 1/2 on this axis right here. Here's some sort of square. And then you would actually be able to make a statement, because let's say in group 2, if you had around 16, let's say we varied from 16 to, I don't know, 20, you could then go over to your line here, then back down to here. And that corresponds then to a range of Weber numbers. And for blood, right, if you remember, if this slope then is actually the square root of what? Rho diameter sigma. So if this diameter actually is seemingly constant around here, then this would actually be, then this value is a constant value. So this is sort of a function of blood. Right, independent. And really what mattered was the velocity down here. So number of splines would correspond to some initial impact of velocity. Okay, and then really if you then just solve, if you imagine the function is this line, you can invert and then figure out then what the incoming velocity was. And it's fun to do if you just go, okay, well that means my incoming velocities, right, sort of number like that. Okay, and you would see, right, that for group 2, sort of the maximum range of splines you have, you would find that it's around like 1 to 2 meters per second is the impact velocity that would have had to occur in your crime scene. And you would know that a gunshot or some whipping weapon of a blood spatter is too, right, there's no gun involved. It was just slightly dripping fluid. And you know that based on all this idea of dimensional analysis of what you've had, right? Because this means, right, this sort of things is this is too slow. Right? You know based on just the number of splines that you saw in all of your data and images that you have. And then you posited and you did this experiment where you varied the Weber numbers and you just took images and looked at the number of splines. That's your scientific conclusion. And you go, you know what? If I only saw about 16 to 20 splines in that crime scene, there couldn't have been a weapon. The blood droplets aren't going quick enough. I would have seen more of these. It would have been much more splattered out. And there's a ton of assumptions that go in this, right, that I didn't go over, but it's still just amazing to me that just from like looking at units and non-dimensionalizing everything in them, that you could then make this statement. It ends up being true. Right? I'm not just making this stuff up. This actually is a true thing that Taylor did and it ended up being right. And this actually is a true relationship that they've done in measurements. I think Santiago at Stanford has a great book where he goes over these examples. And he actually shows the data. But I have a whiteboard, so I can't like pop up the data. But these things have papers where they actually show that they're totally correct. Right? And certainly they would be, because this is based on the idea of making an experiment from the start. And you're motivated by ends easy to observe, right? Just dimensional analysis. Now, other thing, right, keep in mind, we also reduce the dimensions of the problem, right? Non-dimensionalization reduces, right? If you have 5 dimensions, if you have 5 variables that are dimensional, I can take away 3. So then I can have two independent non-dimensional parameters. That's the Buckingham pi thing. All right. Now how about this one's is much crazier, I think. So now let's talk about the number of legs on a swimming little bug in water, or some motion or something like that. okay? Okay. The question is, do bugs with more legs and longer bodies swim faster than small bugs with less legs, or actually the same? So if a bug has, so it seems like yes, but maybe by how much then? So there's a bug swimming in water with a lot more legs, swim a lot faster than a bug swimming in water with the same, let's say, dimension, but less legs. Right? By how much faster? What's the benefit of having more legs and cilia to swim through the fluid? Right? It's not intuitive, I think, maybe because, well, each leg actually corresponds to amount of mass too. The more legs you have, the more mass of the leg you're going to take on. So there is certainly some trade-off that's going to be happening. Right? Bugs aren't packed with a huge amount of legs on them when they're swimming through micro water, but they certainly end up seemingly have a lot. So can we make a statement based on that? So just like that, what would you think is a good function to measure? Well, I think n again, right? You can observe many different species of bugs swimming in water, and you can take a picture. You can just count n. That's not that big of a problem. And then again, we then have a lot more now to keep track of. Okay, there's certainly going to be the density of the fluid they're in. What else do we have? Right, there's their length. There's the bug length scale. There's about some length scale describing the relative size of this bug that we're talking about. Since we are on Earth, right? There's the weight of a leg, as we were thinking about that, right? Yeah. So each leg has some weight. It's really a mass of leg times gravity. So each little bug leg will have a mass associated to it, which causes a weight force. Anything else we could have? Weight of a leg, velocities, and legs. So that means gravity. Gravity's a term there as well. Oh, I should be listing things out. What am I doing? Clearly the velocity is a parameter, right? I can look at a bug and I can see what its usual traveling velocity is, so I could measure that. Density of the fluid I'm going to have all the time. That length scale, just length of the bug, not that hard to get. I have some weight forces. There's the weight force of each leg, and then I'm going to have total weight. Oh, and then this is non-intuitive too. You have, well, each leg corresponds to, let's say, a section of the bug. Also the weight of that bug. You have to go along with why you would reason that idea. Really, the idea is you're trying to see what is the benefit of getting more legs, right, in terms of power, something like that. So I want to talk about the mass of a leg because I'm trying to answer this question of how many more legs should I have if I'm trying to go faster? Does it matter? So you go, okay, well, each leg has a weight, and then each leg would then be connected to a section of body that's contributing to the total mass of the bug. I mean, really, you would say this because, well, there's a total weight of the bug. And one way to say the total weight of the bug would be the n, number of legs. Right? So I've just rewritten the weight force of the bug in terms of these two parameters. Why would I want to separate them? Well, maybe you're just intuitive enough to think going like, well, if I'm trying to experiment on what's the point of having more legs, I probably should write the total weight in terms of a leg. But then I also have to write it in terms of the weight of the mass section on the bug. So I got two more. Gravitational constant. What if it's bugs on Mars? Would they have different behaviors? Interesting topic, right? How about viscosity of the liquid too? They could be they're swimming through some viscous fluid, let's say. It could be water, right? Usually water, right? But have it in there. You could have surface tension too, but there's not any interface happening right here. The bug is submerged. So the surface tension would be what then? Well, you could put it in there and you could look at it, but right, it's not relevant physics is the biggest point about it. Right? You could say it's a small length scale. Surface tension is going to matter. These look really small. But the problem is that the interface is at the top, right? Surface tension talks about an interface happening on a liquid, right? Here's the liquid, right? Here's gas or solid. Right? Surface tension is talking about the force of this interface stretching or right, this interface between the two phases stretching or shrinking. So it's not involved in here at all in this problem I have, so don't write sigma down. It's more units to track that could put you off course. It's this theory of relevancy when you do this stuff. Only talk about the relevant physics that probably are going to happen. Okay. And then there's one more. Yeah, and this is the hardest one, I think. That is power. Right, that is the power output of one leg of the bug. How much power is one leg producing for this bug? Not an easy question, okay? So now here's a bunch. Okay? And there's a bunch more that goes into this, I think. Right? Sort of issues coming around is, right, even if you do Buckingham pi, right, I know I'm only going to be able to remove, right, at most 3, so that's still far more than I have to keep track of. I'd like to reduce more and more down. So we're getting at the edge of this idea of, you know, I think we're getting at the end of the line for some of this stuff for this one example. This is the worst one I could find, I think, where it's like, I mean, I guess you've described it the unit analysis, but you really pushed it. I like the explosion one best, but this one's crazy. All right, so I have power, I have these weights, I have gravity, etc. Now you're just going to play the exact same game here, right? And you have to then look for maybe other references. So you have, what's the reference power? Right? A power is a force time, right? Force dot with a velocity. Okay, and that would be an area times some reference pressure, right, times this velocity. And what's a reference pressure? Okay, reference pressure, you have to think is that dynamic pressure, because of the pressure associated with the movement, right? So that's how you get this. You would divide it by n. Because each leg, right, so NP, right, the total power of all the legs is n times each power of the leg, let's say. So you can divide this out. And then you have this, which is just the rho v squared. So the rho v squared is that pressure, the dynamic pressure. And then you have, let's have force scales. What should my forces scale by? Well, you could have rho L V, but also you could scale by a weight or a volume force, right? All these would be divided by n, actually, for a total. But if you think of it as a per leg basis, so what's the force on any leg, or any force associated to a leg, I should normalize or as a reference to either a weight force, right, a buoyancy force. That would be this rho L squared times the g. It's a buoyancy force. That's fine. You could then scale some things away as well if you did it that way. What's another way you could peruse around this and try to make all the arguments non-dimensional? Well, you could have that this length, right, that the L dimensions of the scale is length, time scale as velocity, and then my mass should probably scale as, right, my density, right, density of the bug. Right. Well, this is really right. This is a mass to scale by, and really it's you have a buoyancy force coming from there. Okay, but then let's just jump along to the chase because again we're at the end of the road here. I think for this you're going to have then. What did I have here? NP rho L squared velocity cubed, and then here's n. And then a Freud number. Okay, so that's sort of at the end of the day for this dimensional analysis. They're just playing around with these dimensions, I think. I mean, right? You could have said at the beginning of all this analysis, I have the weight of the bug. And that's really what I've written here, but you just combined them, okay? And then you end up getting a Reynolds number pops up, and then a Freud number pops up. And then you have this. Well, I've dropped a couple things down, and there were other ones along in there. I mean, there's a dimensionless length, but who cares? So you could divide this by 1. It's even trickier, sort of, right? You could normalize this, and then you get to this point when some people say that, like, well, this is just some other function. Let's say a theta star. So this is 1, right? And now I have this. And then there's the Reynolds number, et cetera. But then you need to take pause at this step, because then you need to remember that a coefficient of drag, right? There's some drag force that the bug has to overcome to go as fast as it's going, to at least generate that power. That's undergrad 2. What's the power of a moving plane is related to that drag force. It has to at least be that power. Okay, so the drag force is dependent, right, on what? That coefficient of drag that you maybe researched a lot. And if you remember, the coefficient of drag may be depending on something, right, on whoever, right, taught, right? But the coefficient of drag, right, is a function of only Reynolds and the Freud number. The Freud number is about the oscillate. So, right, the coefficient of drag is a function of the Reynolds number and this Freud, but you never really saw it before. So that's this idea that, well, if these are two functions, then you can go like, aha, so this is the other parameter is actually this coefficient of drag that's in there. Getting really shifty now. And losing everyone right now, because it's like, how would you know to say that? Right? You could just do Buckingham Pi actually for all these groups if you wanted them to. But I like playing around with dimensions and seeing what works. I mean, this is a power divided by, right, the power, right? This is the power, right, the power of each leg, right, overcoming the power of the dynamic pressure force. There's a normalized weight force by a buoyancy force. It's not that. So now this is a constant value. You would then have to maybe do experiments or see over the length scales of these bugs that this number is basically constant as 2. You have to do experiments then to see that the coefficient of drag for all these parameters you basically see end up being constant. So this is a constant value as well. Okay? And then you get to this issue where I've seen in this example, I think it's McMahon actually did this analysis. Okay, then you get to this part where you say, well, I have a constant on the inside, constant on the outside. So then you say that these two things have to be constant as well. Why would that be? Right? Well, there's the idea, right? There's sort of, I don't know. It seemingly says people just come up with these intuitions because it just ends up working, right? You certainly could, right, do the experiment and notice that it just seems no matter what, it just seems these things are equal to a constant. But obviously, if this is a function, you take inputs into it. It has to be one number, right? I mean, you can see that if I'm defining this function right here to be a constant no matter what I plug into it, right? You can think of it as a boring function, or you can think of it as, well, that means that these are just evaluated at 1 point. A function evaluated at 1 point is a number. So you can go, oh, that would have to mean that these are just, right, these are just have to be constant values. Okay. Power. Okay, and that's just a constant here and a constant there. So now I have two relationships for these constant values that I have. Okay, so now the last step then is you said, well, if these are two constants, and I'm really looking then for some relationship about what velocity looks like, independent of the bug size. Well, I have two equations and two unknowns. I told you your bag of tricks should always be identifying this concept of, I would like to know some relationship, right, independent of the velocities, or independent of the length scale of the bug. Okay. And if you do this, you solve one for the other, maybe do that at extra credit. Show then that get this relationship. If you want to go faster in this bug, it's proportional to some number depending on all the rest of the stuff. I haven't given it yet. Maybe I'll do it in the next lecture. To the 9th root of the number of legs you have. Would you have guessed that? I wouldn't have guessed that. Is it true? It's true for a couple points. And that's the next thing we should maybe get to about this scary thing that maybe you should be cautious about using all the time. Okay? The biggest problem being is it's really, really hard, right, to see the differences for 9th roots of things, right? I mean, you would need to find so many bugs with millions of legs to really compare this. Because once you take the 9th root, you drop the value of that number by a lot. So it's hard to do this. So even though the dimensional analysis is correct and sound, at least, because you just made a function and you looked at all the parameters and you did Buckingham pi, you played around with the dimensions in them, and then you got new parameters, you made some argument of 1 and 1, so that's fine, and it's all dimensions, and then you have this idea that they're constants. You came to this conclusion. Is it testable? Kind of. You can look at data, and this actually does match up for like a couple points of rowers, actually. It works. And then even for some bugs, I see that the same relationship holds, too. But it's kind of a bit difficult to expand this, you know? And just think about the number of n that you have in there, right? I mean, I think I had this example of, right? Look, you would have to, many, many times over, like one velocity has c naught, and it has 100 times more, right, legs than this one. Right, so say there's a bug that has n legs. You would need to look for another bug that has 100 times more legs than it. So if it had 10 legs, that's a whole, if most bugs have, like, let's say 20 or 100 legs, you would now need to find some weird bug that has way, way more legs to verify this. And then even still, that ratio, right, is only, right, this is like 1.6. It's only going about 60% faster, which is like still, you know, you probably could only find 2 bugs that would maybe agree with this. And then if it didn't go by 60%, you know, it's just not enough data, I think, to say anything. If you found one case where it didn't agree, well, it doesn't mean that like it's not true, but it's just not testable. So some of the cons of this unit analysis of just positing functions, naming the inputs, and just like, blah, it has to be this way because of dimensions, is tricky because you can get into situations like this where you come up with a conclusion that's really hard to test. Okay? This is actually the example, by the way, of like the machine learning thing I did. Is I have some of this data of drops that you can do, and you can give the data to a model in machine learning, right? Where before I just had this as n and all of those parameters, right? What did I have this before? I think I had rho. Right? It's had 5, right? What machine learning is it says you know a bunch of these numbers and you know all the inputs, but what's phi? So phi gives you, right? So machine learning models, what they do is they tell you, right? The idea is if you know enough of input and output, I can tell you what the phi is. But this would be different because I would just plug, right? All I would do is I would have to try and vary all of these things and then figure out what the n is. And then you could have your machine learning model tell you the relationship, but it would do it in this space of 5 variables. It does not know, right? Right? If you did have all this data, it can't figure out that really the Weber number is the most important parameter to look at. And that's like the one thing where maybe I don't think, you know, at least fluids-wise, I do think machine learning is super helpful. But for things like this, your computer can't even tell you that that's the important parameter. And that's the one I care about, because what the Weber number has is a physical intuition. The Weber number tells you, is it the surface energy or the kinetic energy that matters more in the drop? So I get intuition from this. You don't get intuition from your machine learning code, right? It's just data and output and then my model that gives you an accurate estimation. So I got to run it every time. Not with the Weber number. The Weber number will tell you, it's a very surface tension heavy drop, going to get less ends. You just know it. Okay, that was a little soapbox on machinery learning, which is great stuff. But with this fluid stuff and dimensional analysis, realize it does more for you than just asking the computer what's this function based on all my data and output. It does a lot more for you. Okay, but there certainly are some cons with all this stuff I've put up on the board, especially because I went over all the details, which you probably are angry about me, of like actually getting the dimensions out of there. Why did I leave out all those calculations and details? Well, there's Mathematica. There's a lot of ways to quickly calculate things, so for God's sakes, just do it. I did it. I don't gotta do it for you. Do it faster than me. Right? Take all these examples and actually play around with the units and get them out of there by hand. Extra credit. Do extra credit. Do it for the energy case. I actually did the energy case. Okay. Extra credit. Do it for the bug case, and then do it for this blood spatter case of just taking the primary dimensions and seeing what's the best primary dimension to eliminate. And then show me all the steps somehow. Even put your mistakes in there, I think. It's fun. People should see that more. But what are the cons we have of this like weird magic method we have of just like looking at the inputs and outputs, saying that has no dimensions, this much has dimensions, I have a tilde thingy going on. Cons are, what do I have the cons on that method is you have to be some genius of physical arguments. I mean, oh, that one's the best case of this bug thing. I had to go through so many different things going like, well, it's the weight, well, it's the buoyancy force, well, it's this, well, it's that. Okay, what if you're not a genius? Well, you're crap out of luck, right? A lot of hand waving, which is, you know, it can be fun later if you know things works, right? Also, like, why neglect in that example? Okay, why do we do that? I don't really know. Maybe you run the experiment, you know to do that. And then the other thing is this whole, like, that's sort of why were the inputs. Sort of this whole thing. Why did I do that part again? There's a lot of cons, I think, of this approach, but they're good enough. So that's where it comes into, this stuff is really helpful if you have a governing equation to make non-dimensional. Okay, the governing equation is sort of telling you the structural form of what the dependencies are, and then you making it non-dimensional is a far easier way to guide you to the answer. Okay, so that last example. Well, let's do this. So have a, right? Okay. This is right, you just go to the laws of force first. Let's look at my force law right here. We didn't even make it non-dimensional yet. Let's just look at the governing equation and consider the scales of things happening in there. Man, I am just so slow for this one. Okay, maybe because it's not intuitive. Okay, so then you have this idea that I have a buoyancy force. Okay, that's really the force law of this bug. I have buoyancy forces. I have the thrust force of each leg, and I have this I have the weight force, and it's going at a constant velocity, let's say. So the ma is equals 0. Okay. Really, what we're talking about is I'm looking for the dynamics when all these things are balanced, when the buoyancy force and the weight force and each of the leg forces matter. Okay. So then you have this relationship of thrusts, and then you have this relationship of forces. And then another one could be then a form of energy. Okay? And that's really then, right? So force, I should say, a force law. Just go to the equation, just Newton's law on that bug, and look at the forces involved. Then we go to scales later. And then for conservation of energy per unit time, you'd have that the power developed by the bug should balance the power, right? The power provided by the bug would be equal to the power that would be taken away, or the dissipation of the drag, dissipation of energy due to viscous forces. Okay? I mean, it's just two equations. You just have to know that there's some viscous dissipation of energy. And that would be this balance that's happening right here. But it's at least more guided. You just need to know this idea of energy per unit time, which is rate power, watts. And then you have this thing. So then the whole, the big shebang is this idea that you have all of these, you have all these balancing, and then you have this power. So this is, this relationship ends up being this. Whole power of the bug is n power developed by each leg, and then the viscous dissipation is related to the drag force. Drag is a result of viscous dissipation. You then know to involve this coefficient of drag, rho, v, and the L's that are in there as well. Okay, and then replacing this L. Okay, then by replacing this L, you go to the buoyancy force concept. That is going this. The weight of the liquid displaced. That's what buoyancy force is. There. So that's a balance of these two things. So this concludes here, where I know that a relationship for the L is n. Okay, and then here goes into there. Okay, and then done. Same relationship. And now you know actually what this is. Where did it come from? It came from a force balance. It came from conservation. It came from the forces involved, and it came from the energies involved. The scaling I then did in my head for that situation was, okay, for my bug, I'm going to look at the forces, and I'm going to want my buoyancy force and my weight force of the bug to balance. I don't want them to be on the same order. And they're both right. You could also say that this balances to this and this balances to this, so that means these have to balance. It's a transitivity rule. And then you get a relationship for the L. And then you use energy, I know that the power of the bug and the whole total power of the bug, or energy provided by the bug, I'm going to say is dissipated in the drag force. It has to overcome that to move through the fluid that I'm talking about. So then I have there. And then you just get these more natural things to solve to come up with the relationships. You get the same thing, that they're going to go faster, but by the 1/9 root. Okay? A bit better. Now let's use a little bit more of this dimension and kind of go to think about viscosity. This is an interesting one as well. Okay? So for a Newtonian fluid, this is sort of starting of another example, This was the concept and law we talked about for Newtonian fluid, Newtonian assumption we had on the fluid. Okay, what are the physical origins of that number mu? Where does it come from, So this relationship comes from some continuum hypothesis I've made on the fluid, and I'm just maybe ask yourself, well, where does this come from? I could measure it at every point in time. It seems to be working pretty well. What's the physical origins of that? So one way to maybe say this is then to look at when does this stop? Let's look at this. When does this stop being true? What's the smallest length scale that can be true at? Well, if it's motion of a liquid, you could have, here's a bunch of molecules of liquid, Eventually, if I zoom in closer and closer and closer, I will not have the equations I talked about, because the entire time I made this assumption that it's continuous. But if I keep zooming closer and closer and closer, that will not be true. Eventually, it will just look like a bunch of rigid molecules bouncing around. So there is then some, let's say, minimum length scale where this would retain its truth, this law of a Newtonian fluid. And I'm looking for that. And then maybe that will help me decide how I could maybe calculate something like this. Okay, so what is the smallest length L where that law would hold? When would the continuum basically be the same? Where I could then think of this still as some continuous motion. and not the case of, right, a bunch of molecules. So that's this idea of, that would be, it still works if all of these are, if really there's still repulsive force, etc. You're looking for a length of, like, when does it kind of look like a bunch of bodies connected by springs, where this spring is sort of the attractive force of these molecules. Okay? So I have this molecule model where there's a chain length, etc. And I'm looking for what's this L. So then just look at the dimensions now of what we've written up here. So this is a stress, is a force divided by area, and then we have a mu. Okay, this would be an m. Okay, this is just the units of the equation we have. You could stop here and go, oh, those are what the units of this are. But we're not kind of asking that right now. We're kind of looking at, like, what are the actual scales of these primary dimensions, right? So if it's going to be true, and then replace this mass unit of m, well, that would be, right, the mass at my length scale L that I've zoomed into. Right, any mass would be proportional to some density times the length, right, the scale of that dimension cubed. Okay. Moving this over, this is why you come up with this new variable. Okay. And then what is this L over t? Well, an L over t is a velocity scale. And that's this idea where that's the actual velocity I want to talk about. When is this law true at the smallest scale? So I have some small scale of velocity, and I have some small scale of length. Okay? So my velocities, I'm going to say, is going to be scaled by my L and over my t. So then here you have a u naught squared. Okay. Then you get this kind of interesting relationship, right? This kinematic velocity, or is it dynamic velocity? I always forget, actually. I remember it as that. But this ratio, right, could physically be described as some very tiny length scale and some, right, scale of velocity at that length scale. So I could tell you what that is because, well, if I'm looking for this, right, if I'm looking for this value of viscosity, and here's the length scale, let's say that scale is, right, some molecular chain length of the, right, some molecular chain length of the actual fluid. If it was a gas, you'd have to have the mean free, the mean free path is what you'd be looking for. But it's some value of length. And really, they're kind of the same thing. It's the average, right? It's the average length that a molecule travels, right? In the case of a fluid, it travels one of its molecular units. And what's the speed that's associated to that? Well, that's the transfer of force through a bunch of springs. So this speed is actually the speed of, right? It's the speed of sound, right? The speed of transmission in that medium. So if you forget what viscosity is or what the value is, you could actually look up, right, just from this idea, you can actually look up just the speed of sound of water and then the chain length of that liquid, and you could calculate the viscosity this way, just from the units of it. And I think what's interesting here is an example that this even kind of explains why something like glycerin has a much higher level of viscosity. It has about 100 times more viscosity than that of water. Now, this doesn't change based on your fluid, right? This is about the same for all liquids. But you would get about 100 times the value, actually, for glycerin, because it has about 100 times the chain length. You can do that calculation as well. Again, it's just from units that we're getting things like this. Okay. So what the point of that was? The point is just from looking at the units of the definition of viscosity, we could come to some conclusion of how to calculate viscosity. If you're ever lost and forget about it for a liquid, seemingly it seemed like I could just find the chain length in that liquid and then multiply it by the speed of sound in that medium, speed of transmission, and you would get kind of the same thing. I mean, this is sort of within 20% actually error. It's kind of fun. Okay. Let's do more now. Let's talk about back to our Navier-Stokes equations, and let's posit this. And let's do this stuff in terms of there. Okay. So we have these Navier-Stokes equations, and they're nonlinear, right? And where'd the nonlinearity come from? The nonlinearity came from this one. Why did it come from there, right? Because this is actually this. Okay, that's where it is. Right there. So if it wasn't there, then everything actually still would be linear because you would just have the velocity field, right, and it's multiplied through. The problem is one of the equations in the Navier-Stokes equation has this term in there, where I'm going to get squared terms in there, making a nonlinear governing equation. So some people say it's the bad part, right? So here's the bad part. Okay. Now, here comes a question of, for an incompressible liquid flow, when does the nonlinear term, right, for an incompressible fluid, when does this nonlinear term and viscous terms matter at the same scales in time, length, and velocity? It's a question. It's a question of turbulence, actually, right? Because if it's incompressible, what does incompressible really mean? Right? It means that time rate of change of the velocity field is 0, okay? And that actually, right, corresponds to this, right? This is a non-zero number because you can't have a zero density. So that, right, incompressible flow is summarized by this concept. The divergence of my velocity field is 0. And it's an approximation. It's posited that maybe doing this puts you into a bunch of issues because even though it's a very, very tiny number, having it being a non-zero number could be important later on. But seemingly experiment-wise, we're not seeing that the most. Okay, it turns the incompressible condition of actually positing it mathematically, this sense of divergence, turns out to be working pretty well all the time. Okay, and then if you take that assumption and you put it into the right-hand side of the equation form we had last time, you would get the incompressible equation, right, incompressible Navier-Stokes equations, and they are this. Okay, essentially, this canceled out a bunch of terms because it was 0, and you find it popping up in the equation, so kick them out, and then you get that governing equation. That's really my favorite equation because I use the incompressible one all the time. And then you can do even more. Right? We'll also do the exact same thing for our temperature one. And now I'll have to make some assumption on when I posit this question of when do these terms matter or not. Okay. I also should say that that's an adiabatic flow. I'm not pumping a ton of heat into the flow. So that kills off, that kills off that term. And then the beta is actually another compressibility term or a volume expansion. I kill off that term. All right. And then you just have two sort of terms left over, right? And this is right. And this term is a statement about what? It's saying something to you. Once I made that statement that I have an incompressible adiabatic flow, meaning I don't have a giant hot rod in the liquid that's bubbling and putting much heat in there, I get this set of equations, incompressible Navier-Stokes, continuity, and then this. This is amazing already, because this tells me right? This is an energy term due to temperature changes, and this is a viscous stress, right? Work done by viscous forces. So they're called dissipation terms. Okay, so now I know that motion happens due to that top equation. There's a constraint here which killed off a bunch of terms, and because you've restricted where the mass can go and how it's transferred, now you know that the viscous, right, that viscous forces are dissipating the motion energy, whatever that means. But you can see it just right here. You can see that there's motion that occurs, and then that energy, which is the viscous part, is then dissipated out and turned into heat. The transfer of energy goes that way. So then I posit then those same questions: is when does, what are my length scales? What's a time scale? And what's really even a velocity scale? Okay, so there's another thing happening here, right? If I go smaller and smaller in length scales, clearly this will be the case, because this scales by 1 over a length scale squared. So if it's a very tiny number, this matters more than this term over here. Do it by the scales in there. So this question then saying is, when do they meet up? When does my turbulent term meet up with the viscous term and hand off that energy? Very interesting question, I think, and just positing it by the equations of motion. So I've asked you, when do they balance? I had a nonlinear term in there which is really governing a lot of changes in velocity. You get chaotic patterns because of that nonlinear term. Okay? Posited that the problem being, I know that motion of fluid goes on and on and on and on and on, but it seems like I always take a video and it always dies down to nothing. So when did that trade-off happen? What scales did they happen off at? Okay? If I go further and further down, again, think of, delta should scale like a 1 over length. And we can do that later, but I just want to keep going on this. Okay, so right here, should we get at it? Let's get at it. That's again, right? So that's the question I asked first, and it's this idea of turbulence and viscous, or laminar and turbulent flows, right? But even prior to that, I kind of just like looking at the structure of the equations before you get to a Reynolds, and you really just think, when if I go smaller and smaller and smaller in my scales, where is the point when it trades off? When is this actually the equation I have to solve? Right? Everything combined. So what do I have? I think I have, what time is it? I've just been rambling on here. But you know what? Let's have it in the notes. I can do it again. Oh, man. Let's just do it then. All right? So first thing is this is an energy dissipation term. So commonly we call this an epsilon, right? Or just call it a term. Because I don't really actually want to calculate this whole term. I just sort of ended the line of energy transfer at this point. Right? Motion has energy going around everywhere, but at a small enough scale, I get down to this term. So viscous energy dissipating the energy. Right? Viscous forces dissipating my energy. So I have this an E dot, and it scales like that. So let's say this term looks like this term, and then this term right here, which is a gradient over a velocity term like that. Okay. Now I have, if I divide the row out, I have this nu, which we already talked about its origins. And then I have, okay, closer, right? I have some dissipation, and all I've done is inserted scales into here. So my vector u, let's say I just scaled like some value of velocity I have, which I'm also trying to find. And then I have my length scale. What else did you also think that makes this possible, right? again, in your handbag of tricks, I'm looking for L, T, and U naught. So how many equations do I need? I need 3. Do I have 3? 1, 2, and 3. Actually, not 3. This one didn't matter. The other 2 equations I have is I'm saying this. These these terms balance, and these terms balance. How would you know to say that? Well, this is time rate of change, so it's about time. So I'm asking is when is the velocity time rate of change caused by the convective nonlinear term, and when is it caused by the viscous term? So it would mean that these 2 terms balance. So I have this balancing that and have this balancing that. Right? Okay, so I have this balance, and then I have this other balance. Okay. 3. Okay, now we're set up to solve this because I have 3 equations. So I can get an L, a T, and a U based on these equations. So now you back solve and do tricks around here. What does this one say? This one's a pretty stupid one, I think. This says that time scale, right? This says that the time should look like what? It should look like, actually no, this one, what this one actually ends up saying is that. Pretty stupid. It's just saying that my velocity scale is scaling like a length over a time. And now the second one you get okay? So see how in this term, these cancel it out. In this one, you don't because of the square term, right? So here I had rho over time, and now it's scaled as U naught. Okay? Okay, and now you can actually solve for all the terms that we were asking for before, because I just substitute things. I just substitute everything in there, and then you get the Kolmogorov term length scales. He was a very good mathematician, by the way. Right. So I have my length scale is what? Property of the fluid, energy dissipation. You get this interesting. Cube of this viscosity term, and then to the 4th power. And then I have my time scale, right? The pass-off time scale is what? Is this. And then I even have and these are pretty fundamental terms if you study turbulence at all, actually, are these length scales. It's a scale of length, a scale of time, and a scale of velocity. And it's telling you where that energy transfer occurs. So when my length scales and time, so when I have a length scale, a time scale, and a velocity scale all at this level where you have some dissipation of energy, you actually don't know what that is either, which is a tricky thing about it. You just then know that that is where that trade-off happened. If I go any further down, then I'm starting to lessen the effect of the nonlinear term on the left-hand side. And it's being more and more dominated by the viscous term on the right-hand side. How would you tell that? Well, actually, before we get to Reynolds, I would just say, what the Reynolds number at this length scale, right, is by calculation alone, right? This would be a velocity scale times the length divided by that. And if you insert all these things in here, you'll reaffirm that this is actually what you're talking about. They all matter. They all balance. It's 1. It's a scale of Reynolds number equaling 1. So what does that mean? Right? If your length scale says Reynolds number equals 1, that means that there's no difference, or that your equation is treating the effects of inertia and viscous exactly the same. They're on the same order as long as the equation is concerned. Right? I mean, I hope you appreciate the fact that we took our set of equations that we had before, and we just derived a huge fact of turbulence of these energy scales. Right? And a lot of times you're given these scales as like an argument of the energy transfers, of the eddies go into lower and lower terms, and onward, and then viscous takes it and dissipates it into heat. But I do like I do like concluding things from governing equations alone, because I'm not a genius and I can't just say where the energy is going to go. But I could look at this equation and then maybe just say, when would my nonlinear term, right, matter as much as this viscous term? Right, essentially, you are saying, when do I have, when in terms of in terms of the time-changing dynamics of my velocity, when is this term really on the same effect as this? And that's a balance equation, and I can do that. And then you have a compressibility term, which simplifies my energy term. And then from there, you even see this viscous dissipation into heat. Because all that's left over, if it's an adiabatic flow, is the viscous dissipation term and then the heat term. So what does that tell you? It tells you then that those viscous forces have to be dissipated into the heat of the flow. That's adiabatic. And then just from that, and just running these rules of I want these things to, I want these two terms of balance, and I want these two terms of balance, you get systems of equations, and you solve them, and you find a length scale, a time scale, and a velocity scale. That's the scale of the turbulence where that thing has happened. We won't talk too much about turbulence, but I think that's fun to do just based on the dimensions of our problem so far. We've only talked about dimensions. So it seems to be helpful, so I want to, let's do that then too. Let's non-dimensionalize. Let's look at what Navier-Stokes looks like if it is non-dimensional. Certainly the incompressible one is nice. Okay? Okay, this was incompressible. You can get to it. Oh, I haven't gotten there yet. You can get to it, I believe you can, from incompressibility now. Great, because incompressibility is a statement saying that the density field is a non-changing, it doesn't change. It's a body force gravity. So this is the incompressible, this is the incompressible Navier-Stokes equations, where you removed a bunch of terms because the divergence of the velocity field was 0. Okay, so let's read, if you make these non-dimensional, you have some things to do right now. Well, there's time scales and a bunch of else, there's a bunch of time scales I have to use. So what's some natural choices? Well, let's think of it this way. This, is some sort of operator like this. Okay, so whenever this pops up, you can go, well, I'll just this is a column vector, but you could just say, well, I'm going to say that looks like, anywhere you see one of these, you just replace it with like a 1 over a length scale, right? Because they're all dimensions of length. It could be a vector. If you don't care too much, I mean, you could just actually have this be the norm, of this. So say there was a x dimension, a y dimension, and a z dimension. Okay? If there was one of those, then you would insert those into this vector operator, So then you would have, let's say, where the stars represent non-dimensional values of length. So now this operator, if I inserted my scales, this meaning that like, okay, well, this dimensional value of x is some capital X times some non-dimensional scale of x, or how I'm measuring coordinates. So you can set that in, right? So then this could also be thought of then as actually this row vector times okay? And that's because it's defined as a row vector. So if I want to reaffirm this non-dimensional thing, you have to use a matrix, right? So this is actually my non-dimensional gradient operator. And then this matrix, which has dimensional scales in it, okay? Capital X, capital Y, capital Z. All right? Now, go back to what was volume, right? If you go back to what was like the volume expansion of something, 151, I'm already late again. Oh my God, sorry. I did talk about the extra credits, so maybe I don't want to rush. I want to do my heat transfer problem too. No. Okay, back to this though. You had dimensional gradient operator. You use this idea of non-dimensional x, y's, and z's, and now you have this thing hanging outside, which is the identity matrix. Could be a tensor as well. Hello, Jacob. Okay. So now you have this thing here, and then you go, well, what's the scale for this? Well, right, this is the, you could pick a bunch, right? You could just have the trace of these, right? You could have the trace of this matrix. I mean, the scale of this is some invariant of these quantities. So you could just have, right, what is the, I'm getting at what is this length right here? Well, this length could be made up of these diagonal entries of your scales that you've picked. Okay? So it could just be, right, this 1 over x plus, right? So this would be the trace of this matrix here. Either way, there is just some L that you could define it as, and it would just give you some approximation. I mean, even so, right, this dimensional, right, this trace, this matrix, right, if I just add them up, which is just the trace of the matrix, which is a measure, right, of the operation of it, don't worry about that, right, you can even see how really large scales kill terms off in here. Really small scales blow them up, right? If y and z are very, very large length scales, it really just looks like 1 over x. If these two are the same and this one's big, right, this one kills off and these two matter most numerically. But it just all plays out there. Either way, I'm going to call this L. That's my L. So all that to say, where you see these, pop that bad boy in there. Okay? There's a little more to do. What's a pressure? What pressure should we normalize by? There are options. This is a right? This is a non-unique question. Okay? One pressure to normalize if I want to care, let's say, about this term. Okay, right? Again, we know what to insert for here. We now need a pressure to normalize by, right? We want to write this, my dimensional pressure is equal to some non-dimensional pressure times a scale. Question being, what should I use for my non-dimensional, for my reference pressure? Well, just as we did before, I think it's a good one to pick if we look at the nonlinear term too. Because I want to describe everything going on continuously through my equation. I don't want to just throw away the nonlinear term whenever. I should kind of keep it in there. Okay? So kind of putting this out again. You have this row. Always just... Okay? So this is the problem term, right? So that's right. That ends up scale-wise. Why not use a dynamic pressure? Right? There is a dynamic pressure in there. I've already made an assignment for this. This is going to look like 1 over L. Can't change that. But then look what's left over. I have a row and then like a u naught squared. right? What is that? That's dynamic pressure. So that's one reason that we always choose the dynamic pressure to normalize by. It's because you don't want to just throw away the nonlinear term, so you should keep it around. Other reasons are dynamic pressure measures the effect of the motion of the fluid. So if I normalize by it, I'm retaining this pressure field in there. This pressure is actually, I have to put this tilde in there because this is actually the summation of the thermodynamic and the mechanical pressure. But you want to keep the effect of that and how it's distributed to the nonlinear term and the laminar term. But you don't have to do that. You could normalize pressure by a surface tension. So if I have some pressure here, I could say it actually normalizes by sigma over 2r. And that being the fact that if you have a bubble, right, you maybe done this thing where you get this result where, right, this pressure of a bubble surface happening in there is this 2 over r, associated because there's a phase change. But that's another choice you have. We don't do that right now, and that will be left for the surface tension section of this class. We will normalize by that dynamic pressure. So what do we have? We have okay. So that operation, gradients are by a 1 over an L, okay? And then I have, right, time will be that L over my scale velocity. Scale velocity is also something I've just inserted in there. And then sort of last is this pressure scales. Pretty natural things to do for the equation structure, right? I've said I'm just putting this insertion of how, right, if I'm looking at rates of change depending on what scale I have to talk about this. Again, this had the x's and it's well defined. This time was this, and then this pressure I've decided to make this because I want to retain nonlinearity in the motion equations. And then if you've never done this before, I think it's always just good to do, right? If you insert it, you get the non-dimensional form, right? So that means, let's say, this is a non-dimensional form of the equation, right? And here you have 1 over Reynolds and this 1 over the Freud number, where the Reynolds, right, is just this is just the term that popped up in front of there, and it's right that, and then you define this Freud number as that. Now maybe there's a better explanation of what you've heard all this time of Reynolds numbers being big or Reynolds numbers being very, very small. In case of the non-dimensional term, meaning whatever dimension I write this equation as, I still want it to be true, you would have this case of, well, if the scale of my velocity is really, really big, right, more so than the length in this term will die off. Okay, and I'll be left with just this wholly nonlinear term on the left-hand side. Likewise, if I have extremely tiny length scales, highly viscous fluids, super slow-moving fluids, what happens? This r goes to 0, blowing up this term. Don't care about that one, and now I have a normalization of this term. Okay. And then there's the other case of when it was equal to 1. And we found when it was equal to 1, and it answered a natural question of when was the energy exchanged. And you saw it happen right before your eyes. Okay. That's fun. I think you see it then. You see where the Reynolds number is coming from. It comes from non-dimensionalization of equations. Okay. I'm at 2 hours now, and I'm just going to stop. And I have these more examples of inserting scales into equations in my notes. And I'm going to stop at 2 hours just because I shouldn't make a habit of going over. But look over the notes then on the heat transfer and maybe posit some questions to me about why that would be the case. Or more so, put some things on Slack to say, just keep going, Sam, just keep going on the lectures, and we want to watch them. But if you're not watching them and you find me confusing talking up here, then just let me know and I'll just stop at 2 hours and it will make everyone's life easier. So maybe just tell me, just let me know on that next class, or just on Slack. If you want me to just go over and keep talking about stuff, or you'd rather me just stop because you're not really watching it anyway. Just let me know, honestly, okay?